Why do pendulums not stop when they reach equilibrium? Any ideas? Joey?
There's no force stopping it.
Bingo! We just said that the force at equilibrium is 0. So if there's no force at equilibrium, there's no force to stop it. So if there's no force to stop it, it just keeps going. That's why pendulums will go for an extremely long period of time. You'll notice my pendulum up front is swinging. I started it about 7 minutes ago. It's still going. Now, it's much less than it used to be because there is friction at the top where it swings back and forth. So it is going to slow down. There's also air resistance. But it will go for a really long time. All right, use your lab to explain whether or not it's affected by gravity. So we did part B on the lab, and in part B we solved for G, and most of you found that your G values were pretty close to what we thought gravity would be, close to 9.8. So is it affected by gravity? Yes. So gravity checked out in lab B. So we did gravity in lab B, and it came out that yes, we got the number we should. If gravity didn't work, then we wouldn't have gotten that number. We would have gotten something random. All right. What is the equation for the period of a pendulum? Period. So this is the symbol for period. We've done it before, but in case you've forgotten, capital T is period, equals 2 pi times the square root of L over G. L is length. G is the acceleration of gravity, or 9.8. Unless we're on the moon, or Jupiter, or somewhere else. But unless we're somewhere else, it's 9.8. So let's look at an example here so you can see how to solve this. Then we'll talk about simple harmonic motion. Then you can work on the practice. So number 7, what is the length of a pendulum that has a period of 0.5 seconds? So, period, 0.5 seconds, length, we don't know, and G is 9.8. So, the equation is 0.5 equals 2 pi times the square root of L over 9.8. Now, I purposely picked one that the algebra is tricky on because I want to show you kind of the hardest algebra first so that you can be good on any of the other things it asks you to solve for. Okay? So, first thing we need to do is get the 2 pi to the other side. L is what we're solving for, so we're multiplying L by 2 pi, so we need to get rid of the 2 pi first. So I like to go ahead and multiply 2 pi together. You can use the actual pi number, or you can use 3.14. It doesn't matter. I'm going to go ahead and do 3.14 just so you guys can see how most of you will do it. So that's 6.28. So I'm going to divide both sides by 6.28. So 0.5 divided by 6.28. 6.28 divided by 6.28. So it cancels. Square root of L over 9.8. I'm going to run out of room real fast, aren't I? So 0.5 divided by that value, 0.079. And that equals the square root of L over 9.8. Now, what a lot of people like to do here is try to multiply 9.8 to both sides, which makes sense. You're dividing, so you got to do the opposite. The problem is the opposite is not 9.8 yet. See, we're square rooting it first. So before we can do anything with the 9.8, we got to get rid of the square root. And we do that by squaring everything. We square the right side and we square the left side. So I'm going to square the left side, and when I do that, I get 0.0796 squared, which is 0.0063. And that equals L over 9.8. And now I'm ready to multiply both sides by 9.8. When I do that, I get a length of 0.62. Oh, nope. Just kidding. 0.062 meters. So that's 6 centimeters. There you go. Not all your problems will require this much algebra. Sometimes I'll ask you to solve for period. But I wanted to show you one where you had to solve for length. All right, last thing. Use a pendulum to describe, in general, what simple harmonic motion is. So what things does simple harmonic motion have? So simple harmonic motion has several things. So first of all, it's periodic. It takes the same time to go forwards and backwards. Okay, it has an equilibrium point, just like the pendulum does. And lastly, it has a restoring force. And that's just a force bringing the object back to equilibrium. So an example of something that is simple harmonic motion is a spring. Springs are periodic. They take the same amount of time to go back and forth. Springs have an equilibrium. There's a point where the spring isn't moving. It's just constant. And there's a restoring force. If you stretch the spring out, there's a force to bring it back to equilibrium. An example of something that's not would be a merry-go-round. Merry-go-rounds are periodic. They take the same amount of time to spin around once. But they don't have an equilibrium. There's not one spot where merry-go-rounds stop. It's not like if I stop a merry-go-round, it stops in the same place every time. It stops in a random spot. And it doesn't have a restoring force. There's not a force to bring it back to that point. So while they are periodic, they're not these other two things. You have to be all three things in order to be simple harmonic motion. All right. Take a look at the practice sheet.
Monterey, did you get one of these in the Pendulum?
first of all, you only need to do the front. The back page is on springs, and we haven't talked about springs yet, so don't do the back. Only got to do the front. So on the front, the first couple things are concept questions. So number one, you're just telling me which one is simple harmonic motion and tell me why. The next two, you're telling me how much the period changes if you change something. The easiest way to do this is to use the equation at the bottom of the page and make up numbers and see what happens. Okay? Number 4, 5, and 6 are using the period of a pendulum equation. There's a second equation down here that shows you the force of a pendulum. That's not really important for us. We'll come back to it a little bit later, but that's what you're going to be working on. So go ahead and get started. Use your time wisely. I think you can finish before the end of the period if you use your time wisely. So work through it, see what you're able to come up with. Ask me questions if you have questions, but use this time to try to knock out the practice, see if you can get her done.